Today we will study the topic floating point representation of numbers in the continuation of the study of topic computer arithmetics. There are the two types of the arithmetic operations available in computer. There are integer arithmetic number 1 and number 2 real or floating point arithmetic. Integer arithmetic and the real or floating point arithmetic. Integer arithmetic deals with the integer operands, numbers without fraction parts. It is used mainly in counting as subscript. Number 2 is the real or floating point arithmetic. This arithmetic deals with the fractional part as operands and is used in most computations. In floating point representation, a real number is expressed as a combination of a mantissa and exponent. So in floating point representation, a real number is expressed by the combination of mantissa and exponent. Mantissa is made less than 1 and greater than or equal to 0. This mantissa is the decimal number and the exponent part is the power of 10 which multiplies with the mantissa. So let us take an example. The number here 66.72 into 10 raised to the power 6 is represented in the floating point representation as 0.6672E08. Here this given number we have to represent in the floating point representation. So we have to make it as given number 66.72 in the decimal number by shifting the decimal point towards the left up to two places. So this becomes 0.6572. This is the mantissa, and by shifting the decimal point towards the left up to two places increases the power of 10 by 2 digits. So this 10 raised to the power becomes 10 raised to the power 8. So we can write it as 10 raised to the power 8, 10 raised to the power 8. So we can write it as in the floating point representation as 0.6572 E08. This part represents the mantissa part and this is the exponent part. This exponent part represents the power of 10. Here we have assumed hypothetically that a computer has a memory in which each location can store 6 digits and has provision to store one or more signs. So this number 0.6672 E08 is thus stored in the memory location as shown below. So this is stored in the memory location as decimal point 6672 and 08, where starting 4 digits represent the mantissa and the last 2 digits represent the exponent part. As we have assumed hypothetically that a computer's memory can store 6 digits. In this case, the 6 digits available in a memory location are arbitrarily divided into 2 parts. 4 digits are used for the mantissa and the 2 for the exponent part. The mantissa and the exponent have their own independent signs. We can see here both mantissa parts have the positive sign and also the exponent parts have the positive sign. While storing numbers, the leading digits in the mantissa is always made non-zero. The leading digits in the mantissa is always made non-zero by appropriately shifting it and adjusting the value of the exponent. So, we can see here by this example. Suppose if we have a number 0.006672, this number would be stored in the memory as, by shifting this decimal, we have to make the leading digit of mantissa non-zero. So we shift the decimal point towards the right up to 2 places, and by doing this, 10 raised to the power, we have to multiply this number by 10 raised to the power minus 2. So we can write this number as 0.6672 multiply with 10 raised to the power minus 2. So this mantissa, this gives the mantissa part and this gives the exponent part. So we can write it as this. Here is the decimal point 0.6672, this is the mantissa, and this is the 02. Now coming to the sign, 0.6672 is the positive, so it have the sign positive, and this 10 raised to the power is negative, so here we write the negative sign for the exponent part. This is the representation of 0.006672 in the normalized floating point mode. The shifting of the mantissa to the left till its most significant digits is non-zero is called the normalization. So the process of making the most significant digit of mantissa non-zero is called the normalization, and this is called the this number is called the normalized floating point represented number. When numbers are stored using this notation, the range of numbers magnitude that may be stored are 0.9999 into 10 raised to the power 99 to 0.1000 into 10 raised to the power minus 99. So the range that can be stored using this floating point representation or notation is given here. This is the range, which is obviously much larger than that used in the fixed decimal point notation. This increase in range is obtained at the cost of reducing the numbers of significant digits. After the floating point representation, now come to the arithmetic operations with normalized floating point notation. Arithmetic operations between the normalized floating point notation. Let us start with the addition. If two numbers represented in normalized floating point notation are to be added, the exponent of the two numbers must be made equal and the mantissa shifted appropriately. For example, if we have the two numbers for addition, number 1 is 0.4546 E05 and second number is 0.4533 E07. As we can see here that both the exponents are not equal, so first we have to make both the exponents equal by shifting the number first, by increasing the number first exponent by two numbers and shifting the decimal points towards the left. So 0.4546 E05 can be written as 0.0045 E07, as we have to make the exponents of both numbers equal and the N2 number is 0.4533 E07. Now adding both these numbers, that gives 0.4578 E07. Now taking another example, example number 2. There are the two numbers for the addition. Both numbers have the equal exponents. So exponents are equal, we can directly add them. So that gives the number 0.9979 E05. Now taking another example, example number 3. There are the given two numbers for the addition. As we can see here that both the numbers don't have the same exponent or exponents are not equal. So we make the exponent of first number equal to the exponent of the second number. So E03 first number exponent is 03 and second number exponent is 07. So shifting decimal by 4 places towards the left, as then it increase the exponent by 4 digits, so the exponent become E07. Now adding the both numbers, that give the answer. Again we take next example. Both the number have the same exponent, so we add them. That gives the value 1.1279 E03. Now here mantissa is not normalized and mantissa also have the 5 digits and is greater than 1. So now shifting the decimal towards the left and increasing the exponent by 1, that gives and taking the 4 digits of mantissa that gives the value 0.1127 E04. Due to shifting, the exponent is increased by 1 and the last digit of the mantissa is chopped off here. Now taking example number 5, add these two numbers. Here both the numbers exponent are 99. Now adding both these numbers that give this result. So we can see here the exponent part cannot store more than 2 digits and the numbers here is the largest number. The number is the largest number, or we can say the out of the range of the storage. So this cannot be stored in our hypothetical computer. This condition is called the overflow conditions.